Earlier on, there was a slide which showed that 5% of everything was, us, as it were, the real world that we know. How do you know it's 5% when you don't know what dark matter is made of?
Yeah, good question. So, there are a number of different ways of working out how much dark matter is out there. So there's the lensing method. So you can use this lensing method across the whole sky, essentially, and map the distribution of dark matter by how light is being bent through space, and you can compare how much bending you expect from how much visible material. So that's one way of getting at how much dark matter there is. Another way, the way dark matter was originally observed was by looking at the rotations of stars around galaxies. So a physicist called Vera Rubin in the 70s was looking at Andromeda and other galaxies near to the Earth, and she measured the rotation speeds of the stars. And what you expect is that close to the center of the galaxy, you have lots of gravity, so the stars should be orbiting very quickly in order to not fall into the center, essentially. And then as you move out through the galaxy, gravity gets weaker, and you'd expect stars on the edge of the galaxy to be going around more slowly. And what she found was that the speeds of the stars didn't seem to depend on how far they were from the center. So they fell off a little bit, but more or less they stayed constant at any distance. And that, again, to explain that motion, you need to invoke some invisible material that adds an extra gravitational attraction to hold the stars in the galaxy. And you can use that, again, to measure how much dark matter there is in neighboring galaxies to our own, for example. The other way of doing it is by looking at something called the cosmic microwave background, which is very, very faint microwave radiation left over from the Big Bang. So it's essentially the point at which, just about 380,000 years after the Big Bang, the universe, before that point, was like the sun. It was kind of a boiling mass of superheated plasma. At 380,000 years, it expanded enough and cooled down enough that plasma condensed into a gas, and light, for the first time, could travel freely. And that light's been basically traveling through space ever since, and we now detect it as this very faint echo. And by looking at patterns that this radiation across the whole sky leaves, you can calculate, again, how much dark matter there is in the universe. And all three of these methods give you broadly similar answers. And the dark energy one you can work out by basically how much acceleration is there in the way that galaxies are moving away from our own. So they're all complementary measurements, and they basically all line up. So this is a fairly solid picture, and it's particularly in terms of the dark matter.
Becky, do we have anyone over there? A young man in the middle?
If the theory that gravity leaps through higher dimension is true, wouldn't that mean that there isn't a boson for gravity?
Very good question.
So then how could you explain gravity?
Is there a boson for gravity? Is that what you're asking?
No, but basically, then if there's no boson for gravity, how could you explain it?
Okay, so that's a very good question. So I suppose there's two parts to your question. We asked about extra dimensions. Does that mean there's no boson for gravity? Well, we think there is a particle for gravity, and it would be called the graviton. And it would be a bit unlike the other particles in that table. The problem with gravitons is that, assuming they do exist, and we sort of assume that they do, because gravity is so weak, it's very, very difficult to actually measure their effect. So if you go down to particle level, you've got these incredibly strong forces. You've got the electromagnetic force, you've got the strong nuclear force, and you've got the weak force, and they totally overwhelm gravity. So if you're trying to do some experiment where you're measuring, say, the gravitational attraction between two particles, that attraction is so fantastically tiny that it's basically impossible to measure in an experiment at the moment. If you wanted to really see evidence of gravitons, you have to build a gigantic particle accelerator that was the size of the Milky Way, unfortunately. So we think gravitons are out there, but we don't have any firm evidence for their existence, but it's kind of assumed that they are. But they're very, very, at the moment, impossible to detect directly. But sometimes, actually, these extra-dimensional theories contain massive gravitons in them, and those are things you could observe in a collider. So if some of these extra dimensions of space ideas are right, then there could be gravitons that were detectable at the LHC, for example. So we might find out, maybe, if we're lucky.
Thank you. I've noticed there is a question upstairs. We'll come to you as the very final question, because unfortunately we don't have a microphone upstairs. But is there anyone in the centre block, maybe on the left there? Phil, there's a gentleman right at the back there. I'm sorry to send you right to the top, but we'll all just watch Phil just run up the stairs. There we go.
You said in the Large Hadron Collider there are black holes created, mini black holes that disintegrate into particles spontaneously. But we know there are black holes in the universe at the center of galaxies. Why don't they decay spontaneously too?
That's a good question. Well, they do actually, but just very slowly. So essentially, what Stephen Hawking showed, I think it was in the 60s or 70s, was that a black hole, if you're not feeding it, if it's just sitting in empty space, gently radiates energy away, so it evaporates over very, very long periods of time. So, and the bigger the black hole, the slower the evaporation is. So essentially, as a black hole evaporates, imagine you had a black hole and you left it in space for trillions and trillions and trillions of years. Very gradually, it would give off radiation, and it would get smaller and smaller and smaller. And as it got smaller, the rate it radiated gets higher and higher. So basically, a black hole kind of dies very, very slowly, but then at the last minute, it kind of goes very quickly, and all of its energy disappears, and it'd be a very sort of violent process. So the black holes that we haven't managed, so far there's no evidence that black holes have been created at the LHC. There's certainly no sign of them. But if you could create one of these things, because it's basically as small as it's possible for a black hole to be, it would evaporate instantaneously because of its tiny size, whereas a much bigger black hole would evaporate very, very slowly, and the level of radiation that it gives off is extremely low.
Yeah, I wanted to ask about the Alice experiment. It's a bit of a Cinderella experiment at CERN and doesn't sort of get mentioned very
poor old
often.
Alice, yeah.
Poor Alice. So
yeah.
What's coming out of, colliding heavy ions together? You were going to look for new states of matter. Can you just update us on what's happening with that? And would that have informed our theories? We just had this wonderful discovery of a neutron star merger, multi-messenger astronomy. Has that informed CERN? Has that informed the way our theories of how nuclear synthesis takes place in neutron star mergers?
Really, you're getting at the edge of my knowledge here, to be honest. But I mean, I can tell you a bit about Alice, but neutron star thing, I mean, whether there's a link there, I don't know. There may be. Yeah. But I mean, what Alice does essentially, it's a heavy ion experiment. So usually for about a month of the year, the LHC, rather than accelerating protons, accelerates lead ions. So the nuclei of lead, they're banged into each other. And when that happens, I can't remember what the atomic number of lead is, but it's a big number. Some 100 and something, I can't remember exactly. But when those two things bang into each other, you get a huge amount of mess, essentially. So the Alice collisions, I showed you some of the collisions of CMS. The CMS ones maybe have a few hundred lines in them. The Alice collisions just have thousands of particles going everywhere. So what the objective of Alice is really trying to do is to study a state of matter that hasn't existed in the universe since a very short fraction of a second after the Big Bang. It's something called a quark gluon plasma. So you have states of matter you might be familiar with. You've got solids, liquids, gases. If you take a gas and heat it up even more, eventually the electrons will dissociate from the atoms and you get a plasma. That's what the sun is made of, mostly. If you heat a plasma up even more, eventually at very high temperatures, the nuclei will disintegrate into protons and neutrons. And if you keep heating them up even more, the protons and neutrons melt, effectively, and they turn into a sort of soup of quarks and gluons, which behaves a bit like a liquid. It's kind of this blob of extremely hot liquid. And what Alice is trying to do is really to study the properties of this stuff. So you get, in these lead-ion collisions, you get little blobs of quark-gluon plasma that exist for a very short period of time, and then they condense, effectively, like a kind of a liquid turning into a solid, and the particles come flying out of that blob. And you use what you see in the detector to infer the properties of that very hot blob. And I think, I'm getting this number wrong, but Alice broke the record for the highest man-made temperature ever a few years ago. But I think it was something stupid like 1.5 trillion Kelvin. But don't quote me on that. But it was of that order anyway. So they're doing really extraordinary things. The short answer is I don't know very much about it, but it's very exciting, and it's really telling us something about what the conditions in the universe would have been like very shortly after the Big Bang. And it also helps us to understand this strong nuclear force, because the strong force is actually very hard to study because it's impossible actually to separate quarks out from protons. And the only time this happens is when you make this quark-gluon plasma, where you have this kind of free soup of quarks and gluons floating about. And looking at how it behaves compared to what the strong force tells us, or the theory of the strong force tells us, allows us to also understand a bit more about this force in the standard model.
Going back to the dark matter theory,
Yeah.
you didn't mention the modified Newtonian gravitational theory,
Yeah.
the Mondt.
Yeah.
Is that falling out of favour now?
It's not really been in favour for a long time, I think. So Mondt is essentially when dark matter was discovered, an attempt was made to say, well, actually, let's not invoke a whole new type of invisible material. What if it's just that gravity needs to be modified? We need to change the law of gravity, and maybe we can explain galaxy rotation curves and various other things by just changing Einstein's theory of relativity, general relativity, essentially. And it's always been a bit marginal, but I think, really all the evidence suggests that it doesn't really work. You can't use it to explain all these different things that you see, lensing, rotation curves, the formation of structure in the universe. It's very hard to account for all these different things using these kinds of modified gravitational theories. I think actually that measurement, the neutron star collisions, paid as well, was a really big blow to Mondt theories. So the reason you may have heard about it, was in the news I think a couple of weeks ago. LIGO, which is this gravitational wave detector, saw the sign of two neutron stars banging into each other in a very distant part of the universe, and that causes these ripples in space-time, which can be detected by these incredibly sophisticated, gigantic lasers, essentially, in the States. And what was interesting about the neutron star collision was that it didn't just have a gravitational wave associated with it, it had a light source associated with it. So the two or three things that LIGO had seen before were black hole collisions. When black holes collide, they don't give off any light. They just they give off lots of gravitational waves, but no light. Neutron stars, though, are not black holes. They're made of matter, or very strange and very dense matter. So when they bang into each other, you do get a lot of light produced. So I think when LIGO detected this gravitational wave, they said, look at the sky quickly, and telescopes pointed at the place where they thought the wave had come from, and they saw a glow of light. And what they found was that the arrival time between the light and the gravitational wave was basically exactly the same, within a few seconds. And this gravitational wave had traveled across almost the entire universe. And what that tells us is the speed of gravity and the speed of light is basically the same. And usually in Mondt theories, they're not. So as my understanding of it, at least, is that this really this neutron-neutron star collision actually is a big blow to Mondt theories as well. So they're probably, I suspect they're probably, with any theory, you can find a way of explaining away why you haven't seen any sign of it, but they're not really in favor at the moment.
Okay, thanks.
So are there any questions? There's a gentleman just back. I've had no women ask questions, so I'd like a woman to ask a question if that's possible. There's one there in the middle. Sorry, you're just under the lights, I can't see you. Phil, can you get the mic there?
So you talk about the antimatters. What if they are an anti-force field? Would it be possible? If it is possible, what would it be like?
Anti-force fields. So you mean the so like the photon? Yeah. So the force particles do have antiparticles, but they're actually themselves. So the photon is its own antiparticle. So two photons can annihilate to make an electron and a positron, for example. The same with the gluons, and the same with the W's and the Z's. So they're all their own antiparticles, essentially. Actually, the W is the one where it's really obvious. If I go back one animation. Oops, hang on, too far. There we go. So the W actually comes in two different types, the W plus and the W minus. The W plus is positively charged, W minus is negatively charged. So they are literally antiparticles of each other. But the photon is its own antiparticle. The gluons are their own antiparticles as well. So it's not quite the same, but they do have antiversions.
And the lady in the centre, just pass the mic along.
Thank you. I just want to ask a question about something you mentioned at the start about cosmic energy fields giving mass to all particles. Was it that different particles have different fields, or is it that the field is giving mass to all particles?
Well, so there is a field for every single particle. So every square in this table has a field. So there is an up quark field, for example. And an up quark is just a ripple in the up quark field. And the same for the muon neutrino. There's a muon neutrino field, and the muon neutrino is a little ripple in the muon neutrino field. So those are the fields that these particles exist in. But on top of that, there's another field, which is the Higgs field. And that field, for one thing, the ripple in the Higgs field is the Higgs boson, this thing. But that field also imbues to these other particles the property of mass. So if you like, when you make a little ripple in, say, the up quark field, that interacts with the Higgs field around it, and it acquires mass through that interaction. There's not a very good analogy for it, unfortunately, but that's basically what's going on.
Fantastic. Got about 5-ish minutes left. There's a question here. I'll come up. You can have mine.
Can I ask you a question about dark energy? Dark energy is a field of some sort that opposes gravity, but is energy really the right name for it? Should we be talking about something completely different?
I mean, there are different... I mean, well, everything is energy to some extent. So any field is a form of energy. So there's energy stored in the electromagnetic field, the quark fields, the electron field, and so on. So energy is probably fine because it basically describes pretty much anything you can think of. There's lots of different possibilities for what dark energy could be. One of the first attempts at explaining it was that, well, I said that all of these particles in the standard model have associated fields. And those fields, even when there are no particles in them, so when there's no ripples moving about, these fields have a finite amount of energy, and that's due to something called quantum uncertainty. So because of quantum mechanics, all these fields, if you think about them a bit like the surface of a pond, they're all jittering slightly all the time. And that jittering contains a certain amount of energy. So what people tried to do was to calculate, if I take a cubic meter of space, and I calculate how much energy is stored in all the jitters in all these fields that we've got here, how big is that energy, and could it be dark energy? And what you find, you get a number that is something like 110 to the 120 times too big. So if you basically calculate using the standard, well, a naive version of the standard model, some calculation to estimate roughly how much energy is stored, you find a number that is 10 with 120 zeros after it too large. So if that were dark energy, then the universe would have ripped itself to pieces immediately, essentially. So it may be that it's the energy of the vacuum, which is what we're talking about here, and it's just that we don't really know how to calculate it properly. We're missing something. It could be some additional field, though. So there are various ideas that it could be a field a bit like the Higgs field. So an additional, something that's called the inflaton field, or something else. So which then something that could have been involved in the expansion of the universe very shortly after the Big Bang, and that's been hanging around ever since, and is still causing this expansion. There's some ideas that it even could be the Higgs field itself, that the Higgs field could somehow be causing expansion of the universe. There's loads of ideas out there, but unfortunately no real evidence for any of them just yet.
I'm sure I saw some other hands over there. Who have we got? There's a gentleman there. Thank you.
I was wondering if it's the Higgs field that is what's giving all the other particles mass. How is it that the Higgs boson has an associated mass with it on the diagram there?
The Higgs gives itself mass is the answer to the question, which is maybe a bit unsatisfying. But yeah, the Higgs boson also interacts with the Higgs field and gets mass through its interaction with the Higgs field. You have to take my word for it, unfortunately.
And there was a question just there as well. Yes, you. That's great.
Oh. Hi. Can you talk a bit about you said that Higgs boson imbues mass, and mass is in general is quite related to the gravity, but apparently it's not. So can you talk about that relation?
Yeah. Okay. So let's talk about gravity first. So what Einstein is, well, if we take Newton's law of gravity, what Newton's law of gravity says is that gravity is created by mass. So if I have two masses, mass m1 and mass m2, then there is a force between them which depends on how big those masses are and how far apart they are. So the bigger the mass is, the stronger the force. That's what Newton says. Einstein says something slightly different, which is that it's not just mass, but also all forms of energy and momentum. So if I take a bit of space, let's say I take a piece of the interior of the sun, that contains electrons and protons and other things whizzing about. They all have mass, they have rest mass, but they also have kinetic energy because they're moving, and they have momentum because they're moving about, and they have a pressure as well. So in general relativity, basically all forms of energy are a source of gravitation, not just rest mass. So that means if things are moving about quickly, they contain mass. They create mass as well, or create gravity rather. So that's the relationship between energy and mass. What we're talking about with the Higgs field is we're really talking about the rest mass of these particles. So if I take an electron and I stop it and look at it, it has this fundamental amount of energy left in it when it's not doing anything, which is its rest mass. And that rest mass comes from the Higgs field, but not actually, interestingly, not all mass actually, so not all mass, only this kind of rest mass comes from the Higgs field. So if you have, say, a hot bit of the sun, a lot of the energy in that system that creates gravity is not to do with the rest mass of the particles in it. Actually, interestingly, the proton and the neutron, I said their masses are about 2,000 times the mass of the electron. Protons and neutrons are made of up quarks and down quarks. So here are these two things here. So these have a mass this is in particle physics units, of about 2 mega electron volts, which is about 4 times the mass of the electron. So we've got 4 times the mass we've got 2 of these guys in the proton, so that's about 8 times the mass of the electron. Then you add on this, and that gives you a bit more. That gives you another 8. So about 16 times the mass of the electron. But the proton is 2,000 times heavier. So how does that work? Well, that's because most of the mass of the proton actually doesn't come from the mass of the quarks at all. It comes from the energy stored in the binding of the strong force that glues these quarks together inside the proton. So the Higgs field only really accounts for actually a very small amount of mass. Most of the mass in our bodies is actually the mass of the strong force binding around inside these protons and neutrons. So it explains a particular type of mass, and there is a link to gravitation, but the Higgs field itself doesn't actually do anything different to, say, the electron or to the quarks in terms of adding extra energy that can create gravity.
So I'll take a final question from down here, the gentleman with the mic.
Hi, you said that the Higgs boson was predicted from mathematical equations. I was just wondering, if a lot of these theories are based on maths, why aren't they all correct? Because isn't there only one right answer from mathematical equation?
Well, these are, they're only models. So, maths is the language you use, but they're not derived from first principles. So any theory in physics starts with some assumptions. So, for example, if you take general relativity, Einstein's theory of gravity, that starts from the assumption that acceleration and gravity are indistinguishable. So that's his assumption. And if you use that, you can then with a few other things, you can make progress and derive the theory of gravity. But it's not something that just emerges from mathematics by itself. You could write down lots of different theories, and people do. That's what theorists spend all their days doing, actually, is coming up with some difference. So the standard model starts off with some set of assumptions. Basically, you have to add in different sorts of symmetries of nature and different sorts of particle fields, and then you can use the theory to calculate how these things would behave. But you could equally well put in some different fields like supersymmetry or something else. They're not derived from some single fundamental principle and then everything comes out of it. You have to start somewhere, which is I'm going to introduce these ingredients and then work out what the consequences are. I guess what you're describing is sort of this dream of a final theory that Weinberg and others have talked about for a very long time. Maybe there's some basic principle that if we start with this, we can work out everything, and that seems rather unlikely. I think you're always going to have to make some assumption at the beginning, and that assumption will determine what the theory looks like.
So finally, you've been bursting to ask this question the whole time, so if you could just pass the mic, thank you.
Are we in the 3rd or 4th dimension because of time?
Right, so that's quite a good question. So yeah, there are 3 dimensions of space. There's up, that way, and there's also time. So there are 4 dimensions, but time is quite unlike the 3 dimensions. So spatial dimensions, you can choose how you move through them. So I can go this way, or I can go this way, or I can jump in the air. But I can't choose how I move through time. That seems to just kind of happen. I get carried along through time. And people don't really understand, it's fair to say, very well what time is. And there's lots of ideas about trying to get time to emerge from some deeper principle. But yes, the short answer to your question is yes, there are 4 dimensions, including time. But we don't necessarily really know what time is.
Fantastic. Well, that's a very slightly intriguing but also tantalising point to end this evening. I just wanted to end with a slight comment. As some of you may know, and I may well get the date wrong here, but I think it was 1897 when J.J. Thomson at the Cavendish Laboratory discovered the electron, or as we should correctly say, the fundamental particle that later became known as the electron, which is a very long-winded way of saying he didn't want to call it the electron. Where did he come to announce it? But he came right here to this very lecture theatre to announce the electron discovery. So I like to think, Harry, that when you and your colleagues at the Cavendish Laboratory and the LHCb experiment solve the problem of lepton universality, you'll come back here to announce that discovery. But in the meantime, thank you so much for a fantastic talk and an excellent evening. Thank you.
Thank you.